All right, here we go. So today, we're going to be looking at Chapter 1, Section 3, which is about continuity. So, first thing we want to do is define continuity. And just as a disclaimer, the definition for continuity I'm going to give here is pretty lousy. But that's because to give you a really formal, rigorous definition, I kind of need some calculus concepts to do that. And we're not really ready there. So I'm going to give you a practical, but not very rigorous definition of continuity here. So we say that a function is continuous on a given interval if the function does not appear to break at any point on that interval. So you can see here from this definition with like, what does break mean? Like there's a lot of kind of vague built into this definition that I've given you. It's not very rigorous, but I think for our purposes it's pretty reasonably practical. I think we all have an idea of what we mean by break. Basically, if you can't draw the curve without picking up your pencil, that's kind of what we mean by continuous. So when we say break, what we really kind of are talking about here are discontinuities. So let's look at some types of discontinuity. One of them you should be, I should really say two of them you should be definitely familiar with from last year in Algebra 3-4. Yeah, so when we say holes, I'm going to call that a removable discontinuity. So an example of that might be y equals x squared minus 4x over x minus 2. If I graph that, there'd be like a hole in that graph at the point 2, 4. Now I did that all in my head. It should not, or it need not be obvious to you how I figured that out so quickly. But you should recognize that, oh yeah, I remember when we did talk about rational functions. On occasion there were removable discontinuities. All they looked like was like an open, I graphed them as like an open point on my graph. And that's fine for right now. That's all. To actually locate that removable discontinuity is beyond what I need you to do right now. We did talk about it last year, and I would expect that with like a review of how we do that, you could do it again, but I don't need you to be able to do it again right now. Okay? So this removable discontinuity could be two things. Yeah. Right, so that's what that line is that I've drawn is the graph of x plus 2 with the removal of discontinuity from the reducing at the point 2 comma 4. So that is exactly what happens there, yes. So the reducing is what kind of causes that removal discontinuity. Okay? So your removal discontinuity could look like this, or you could have another point. So the function is defined for all real numbers. But again, this is still a discontinuity because, well, I can't draw that curve without picking up my pencil. Like I can draw the line, but then I need to pick up my pencil to put this other point in. So you may have a removal discontinuity that looks like just an open circle, or you could have an open circle with another point located elsewhere, still removal discontinuity. The second one that Sam mentioned was an asymptote. In this course, I'm going to refer to this as an infinite discontinuity. Let's not do quite that much. That's more than I need. I don't know the world history dates well enough to confirm or deny that statement. So. So you can have a situation like this. We call these an infinite discontinuity because as the graph approaches that asymptote, the ends of the graph are bombing off towards either positive or negative infinity. So they could be going in opposite directions. Or you could have something where they both go in kind of the same direction. Yes, sir. I'm sorry, can you repeat your question? So I'm sorry, guys, I'm just scrolling back to look at. Yes, so this one had two infinite discontinuities, yes. Yeah, at positive 1 and negative 1, yes, David. I just couldn't remember what the prompt for number 8 was to answer that, so I have to go back and look. So if I just do something like this, you can get both of your ends of your graph pointing in the same direction, like towards the same infinity. In this case, both of them are going towards positive infinity, or they could both go to negative infinity, or they could go in opposite directions. It's all still an infinite discontinuity. Is everybody okay with that idea? Okay. There's a third type that you're probably not familiar with, and that's called a jump discontinuity. This is not something that you saw happen in your Algebra 3-4 course. But a jump discontinuity could look something like this, where the graph, there's just like a jump in the graph, that it's continuous before and after that spot, but there's a jump there. Notice here, quite importantly, that one of the endpoints is open and the other endpoint is closed. Why do we need to have one opened and one closed? Good. If they're both closed, it wouldn't be a function, right? Because you'd have one x with two separate y's. Could they both be open? Yes, that would be okay, but they cannot both be closed. If they were both closed, it would not be a function. You'd fail a vertical line test at that specific location. But they could be both open. That is okay. Okay, so let's do some examples here. Everybody feel okay so far? Notice that I didn't really give any formal definitions for any of these. I just kind of drew some pictures. Again, to formally define these things, we kind of need some calculus ideas that are beyond the scope of this class right now. But the picture is one of those you know it when you see it kind of things. They're different enough that shouldn't be an issue, right? Okay. So let's say we have this example here. Where is that at? So I'm just going to sketch the graph really quick. I'm going to use this graphing software that's a little bit gives me a little bit better picture often than the calculator. This is Graphmatica, yes. And let's get rid of that. Get rid of those grid lines. A little easier to see. Okay, so this is the graph of that first example that I just wrote down. I'll go back to it in a second. Is this continuous? No. Okay, what kind of discontinuity does it have? Infinite discontinuity. Asymptote would be fine if you said that too. I'd prefer you say infinite discontinuity, but on a test setting I probably wouldn't be that picky because it's like 6 in one and half dozen in the other. But yes, good. And Bella, here is the function that would pertain to. Let's look at this one. So just like before, I'm just going to, actually let's not do that. No. We'll just type the graph in here and see what it looks like. I need to pick a different color here, I think. Is that a little easier to see? You liked it better before? White? Okay. Okay, is this continuous? Look carefully. Yeah. Go over.
Oh my, I see it. Mr. Jordan, you sneaky. So sneaky.
Yeah, it was removable. I was having... Yes! You could go to the table and look for an error if you suspect that there's a removal discontinuity. That's certainly doable, and if it looks like a straight line but there's an error there somewhere, that's a good indication that what you're looking at is removal discontinuity. Yeah, that's an excellent idea, Joanna. So this one was removable. And the last one... We'll go here. What about this one?
Let's say we have an infinite possibly a 3. How would you acquire the whole bunch?
Well, what if we do a little selective zooming here? What do you, if I give you this picture?
It is not.
Yeah, it looks continuous, right? Yeah, I agree. Little food for thought. What type of function is this? Polynomial. Polynomial is kind of what I was hoping for. Guess what we can say about all polynomial functions? They're continuous everywhere. Okay? You have to do something pretty funky to make it not, like turn it into a piecewise function that we haven't talked about those yet. So, if it's just a polynomial, it's probably fine. So, on to section 4. In section 4, we're going to talk about increasing and decreasing functions, as well as extrema. So, let's do a couple of definitions here. So we can say that a function is increasing on a given interval if for any 2 points on that interval a positive change in x results in a positive change for f of x. So when we say a positive change in x results in a positive change in f of x, what are we really saying there? That for any 2 points that you pick, there's a positive slope. Right? Because what is slope? Rise over run, or change in y over change in x. Everybody okay with that? And certainly positive change over positive change is going to result in a positive slope. Everybody's okay with that idea? Well, if we're talking about a curve, it doesn't necessarily have slope, but if I picked any 2 points on an increasing segment and calculated the slope, that slope would be positive, but the slope doesn't actually apply to the curve. That's what we're saying. Does that make sense? So a little bit different. Stop talking, please, guys. But you get the idea, right? So close, very close, though. All right. We'll do this. And I think, oops. That one. So this is going to be decreasing. And this should be negative. But what are we really talking about here? Yeah. If you pick any 2 points on a decreasing interval and calculate the slope between them, that slope would be negative. And there's one more possibility. That possibility is that the function is constant. If it's constant, there's no change. Okay. Are you guys still copying definitions? I can't tell. Some people are writing, some people aren't. I don't want to move on too fast if you're still struggling to write stuff down. So, yeah, I mean, I'm just, again, like I'm just trying, not to go bulldozing past if some people are still kind of writing here. They are filled in. They're supposed to look filled in. Okay, so let's look at this example. We're just going to identify the intervals that are increasing, decreasing, and constant. Does anyone see an increasing interval? Yes. So this part is the increasing part, right? Is that part there? Everybody agree? Does anyone see a decreasing part? Where's that at? Yeah. So like this part, right? Everybody agree with that? Does anybody see a constant part? Process of elimination, we pick the middle. Everybody agree with that? Okay. So now let's color code our intervals then. So our increasing is the x's that are in what interval? You guys were saying, David, I think you were saying this before, right? Negative infinity to... So should we be referencing an x or a y here on an interval? Always x's. So when we talk about intervals, we're describing the x-axis. So we're always worried about x coordinates. Notice here that I'm not including negative 4 here. Why not? Well, it's because that's where the change is occurring, where it's changing from one kind to the other. We're never going to include any transition points where it's changing from increasing or decreasing or constant, where it's changing from one kind of interval to the other. We wouldn't include those endpoints. Everybody okay with that idea? Okay. The next interval we have is the constant part. How would I write that interval? Negative 4 to 3, and again, not including those negative 4 and positive 3, because that's where the function is transitioning from one kind of interval to the other kind of interval. And then the last part is the decreasing, or positive infinity, I think is what you mean. Again, you're looking at the x-axis. So the interval, and if you're writing an interval, you're always describing the x-axis, even though increasing and decreasing is kind of related to the y-axis. But imagine what we're doing is we're describing like the where is the graph increasing or decreasing. So the where is always about the x-axis.
So we don't have to worry about the brackets?
Well, we had said that any of these transition points we don't include in our intervals.
Okay.
So it's possible you would have a bracket conceivably in this, but I can't think of an obvious example where that would happen right off the top of my head. So probably more often than not, you would just be using a parenthesis, and I'm trying to think if that I could actually cook up an example where you would, not want to do that. And there's nothing obvious comes to mind. So it might be an always situation, but I hesitate to use an always in those for those sorts of questions that if I haven't thought carefully about it. But most of the time I'll give you. How's that? All right, you'll take it. How about this one? That would be the case where maybe we'd have to think a little bit harder about it, and I think having the calculus definition there would be really important in determining whether you should include that or not. Raul? Of course. But yeah, that's the kind of situation where I have to think about it a little bit more, and I would certainly need the rigorous definition to decide whether you needed to do that or not. All right. Let's do it for this one. What are we going to probably need to have in order to do this? We're going to need the picture, yes. So let's go ahead and enter that in. I'm going to type that into Graphmatica. If you have your calculator and you want to follow along on your calculator, I invite you to do so. But I'll type it in here also so that everybody can see it. Did you forget to put a parenthesis around the entire numerator denominator? Huh? If you just press second and y equals, it takes you straight to the fraction menu. That's a little shortcut, so you don't have to jump through so many menus. Yeah. That's just a little shortcut. Some student told me that last year. I'm like, that saves so much time. How did I not know that? If you in this room were that student, I apologize for not remembering giving credit, but I legit don't remember who told me that. All right. So let's take a look at this. Do we see any segments that are increasing here? Okay. Where do we see that's increasing? Negative infinity to negative 3. So we're saying this piece right here. Is there another increasing section?
Yes.
Yes, where I agree. So we'll do a union and then start our next interval here. What section here is that?
Possibly increase from negative 3 to like 3.
Not all the way to 3. Yeah, to 0. Everybody okay with that? And again, if you're having trouble identifying this, imagine you have a little man walking along the curve. When the little man is walking uphill, that's increasing. And when the little man starts walking downhill, that's decreasing. He's walking always from the left to the right, just like we read a book. So here we're walking uphill, here we're walking uphill. But as soon as we get to 0, we start walking downhill, right? Agreed with that? Shh. So my decreasing sections then are 0 to 3, and then 3 to positive infinity. You can name your little man anything you want. I'm going to call him Hans. Yeah. Because, like, it's a good mountain climber name. Like, you live in, like, Swiss Europe or something. Yeah. I don't know about extra credit, but I might laugh if you do it.
Just one extra.
Is everybody okay with what I've done here? Stop talking, please, guys. Question. What if I had written, instead of negative infinity to negative 3 and then negative 3 to 0, what if I just wrote negative infinity to 0? Is that okay? No. Why not? Yeah, so negative 3 is not in the domain, so it can't be included in our interval. You see how there's an asymptote at negative 3? So negative 3 can't be included in our interval, so we have to do 2 sections that are breaking at negative 3. So just to be clear on that, that's a common mistake I see students make. I want to make sure that we mention that. Everybody okay? Okay. Let's talk about then Extrema. So Extrema is a general term that includes either maximums or minimums. So I'm going to just instead define what we mean by maximum and minimum. So we say that a maximum of a function, f, is a value, f of c, that is greater than or equal to all the other range values, i.e. y's, of f on some interval containing c. So there's actually 2 kinds of maximums. Thank you. 2 kinds of maxima. There's a local maximum, and there's also a global maximum. So let me kind of explain the difference. I'm just going to draw some pictures to kind of explain that difference. So if I look at this picture, this this spot right here is a local maximum because there are other y values that are taller than that maximum. But if I pick some interval, like say from here to here, it is the highest point on some subinterval, but it's not the highest point for the entire domain. Okay with that idea? This graph has no global maximum because the graph continues to go up forever. Everybody okay with that idea? Instead, let's say that I have this one. This point here is a local, and this one is a global. Again, the global is the highest of all the y's. A local is high in some little neighborhood around it. Everybody okay with that idea?
So is there a name for the one that's going to be the maximum?
There is no global maximum in that case.
Okay, so it's just local.
Yeah, it just has one local maximum, no globals. So that's a local. Because that end has y values that are bigger than that local, and there is no highest y value there because it's bombing off to positive infinity. So there is no global maximum. Everybody okay with that idea? So we can change the same definition for a minimum by just changing that greater to a less. So in blue is the way we would change that definition to talk about a minimum. In the interest of not writing that all down again, I'm just going to make the two little changes above. Everybody's okay with that? Seems obvious that if I know what a maximum is, the minimum is just like the opposite of it, basically. So let's take the function f of x equals x to the fourth plus 2x cubed minus 4x squared minus 3x plus 1, and try to find the extrema and intervals of increasing and decreasing using our graphing calculator. If we're going to try to use, oh no, where did that go? If we're going to try to use a graphing calculator, what function are we going to have to use to find those extrema? You're going to need to use the min and max commands. You remember where those are located? So from your graph, you press second, and then one of those buttons on the home row, the trace button. And that'll open up the calculate menu, and you'll see the min and max commands in there. Let's see, where is that graphing calculator software? Okay, so hopefully when you type this into your calculator, you got a picture look kind of like this. For whatever reason, I can't find where my graphing calculator simulator software is right now. I'll straighten that out by the next time we meet, though. Oops. Somehow I managed to lose that between last year and this year. It'll turn up. So if we look at maximums, is there any local maxima? Yes. How many? One of them. Is there global maxima? No. Why not? Because both of the ends are pointing up. There's lots of values taller than that local. Are there local minima? Yes. How many? You can count 2. The global are also local, because if you pick an area around it, it's also the shortest one in that area around it. Yep. So this one local and global. If you didn't list it as both, that's okay. If you just called the lowest one global, that's fine. Yes, that would be fine. Yeah. How many intervals do you see that are decreasing? 2. So there's this section here, and then this section there, and then there's 2 that are increasing, right? There's this section here, and then there's this section there. What do you notice about where those intervals of increasing and decreasing start and stop? At the maxes and mins, right? Everybody notice that? So in order to find the intervals of increasing and decreasing, we really got to find the locations of those maxima and minima. That looks like a good place to stop.